Test, test. Audio okay. Let me know if y'all can hear me. Is everything okay? Audio okay? Audio. Let me know if anyone can hear me. I'm trying to check the audio. I'm hoping that it works. All you have to do is just say, yes, I hear you. Can anyone hear me? Can you hear me? Can you hear me? Let me know if the audio is working, because I always have issues with that. I'll even write it down here. Audio okay? Can y'all hear me? Can anyone hear me? Just give me a... here we go. Okay, it looks like no one can... Wait. Y'all can hear me? I'm getting that TikTok is telling me that you cannot. Let me know if you can hear me. Perfect. Okay, perfect. That's just what I wanted to hear. Thank you. Thank you. Awesome. What's going on, everyone? I haven't gone live since, gosh, the AP calculus exam. I've been taking somewhat of a break, but anyway, I'm just, it's summertime. I've been just doing a lot of scribbling here and there. And today I just kind of was, I just made a post on Instagram about the Basel problem. So this summation here of 1 over n squared as n goes to 1 to infinity and y it equals to pi squared over 6. So I'm kind of going to talk about that. So I'm going to talk about that. And most importantly, I'm going to kind of, connect how we get from e to the x to the Euler identity, how we're going to use the Euler formula for some integration techniques, and then we're going to talk about how we get this value here, or we're going to prove why this is equal to pi squared over 6. So again, let me know if you cannot hear me anymore. I hope that you can. And let's just get started. So let's just go ahead and start off with the Maclaurin series for e to the x. And so if you recall, the Maclaurin series is e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x fourth to the 4 or over 4 factorial plus x to the 5th over 5 factorial. And I'm going to write this a couple times. It's going to be x to the 6th over 6 factorial plus x to the 7th over 7 factorial and ... continuing. Okay, the reason why I'm going to do that is because now we're going to go ahead and introduce an I. So I to the x. So now every time we have an input of x, we're going to go ahead and change that and make it an I. So I have I to the x squared, and I'm going to be very careful, make sure I put everything in parentheses. So we have I x to the 3rd power, on and on. Let me go ahead and continue writing that down. So I have I to the 6th over 6 factorial, and so on. I to the x to the 7th factorial, and so on. By the way, again, if you can hear me, let me know. I'm hoping that everything's working just fine. If for whatever reason you cannot hear me, something went wrong. So let me know in the comments whether or not you can hear me. Okay, so now we're going to continue, all right? But before we do that, let's not forget, thank you, Gabby. Let's not forget the properties of I. So remember, I is just equal to I squared is equal to -1, I cubed is equal to -I, and I to the 4th is equal to 1. So this is just going to cycle through. I guess I should have written it sort of like a circle, but it's important to note that because this series is now going to turn into 1. I realized this entire thing, no one was telling me about this. There's an x in here. There should be a 1 plus x in there for all of these. So the series has a 1 plus x squared over 2 factorial. Totally forgot that. But anyway, as we continue, this is going to be ix plus, now we have the ix squared. So if we square the I, it's going to become a negative. So this is going to be negative x squared over 2 factorial. Now when we continue here, I cubed is going to be negative I. So this is going to be negative I x cubed over 3 factorial. And then we have the I to the fourth, which remember, that's just 1. So we have positive x to the fourth over 4 factorial. Now you can sort of follow my math here. This is just going to continue or cycle through. And now this is going to become plus I x to the fifth over 5 factorial minus x to the 6th over 6 factorial minus I x to the 7th over 7 factorial. And this is just going to continue. That pattern will continue. All right, because now what we're going to end up doing is we're going to group these into values that have the imaginary part and those that do not. So in this case, you'll notice we have the 1, the negative x squared over 2 factorial, and then we have the x to the 4th over 4 factorial, and then the x to the 6th. So all the ones that have an even power do not have a imaginary part. So if I group these together, I have 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. And you will continue that process. All the ones or all the even powers do not have an imaginary part. So I can group those together. And then now I'm going to group the ones that do. So I'm going to put an I in the front. And then I notice that the x cubed, the x to the 5th, x to the 7th. So you'll see a pattern here that it's always all the ones that have odd powers that we're going to group together. And basically that's just the rest of the series. So this is going to be x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, on and on. Okay. I'm sure a lot of you guys are already seeing this pattern here. This, if I kind of wrote, or if I write the summation, this right here is going to be the Maclaurin series for cosine. This is just cosine of x plus I times this right here is a Maclaurin series for sine. So here what we have is Euler's formula. I shouldn't have crossed that, but here we have Euler's formula, which is going to be very useful today. And I mean, in so many mathematical, areas or fields. Okay. Talk to Gabby. Talk in the comments. If you have a question, put it in the comments. Gabby can help you. Gabby has volunteered. Anyway, guys, so here we have the Euler formula. Okay. And we're going to definitely use that in a second. We're going to do some integrations involving that. But let's go ahead and talk about how we get the Euler identity. I think we can probably just leave it here or write it down here below. Now, what would happen if I substitute the value of x in for a pi, or substitute the value of pi in for the x? So I'm going to have e to the I pi equals cosine of pi plus I sine of pi. Look at that. Now, sine of pi, that's just going to be 0. Cosine of pi is -1. So we have I to the I pi is equal to -1. And if some people have done polar coordinates, or some people are familiar with complex analysis, I mean, this is a very simple identity that e to the I pi is equal to -1. We bring the 1 to the other side, and guess what? E to the I pi plus 1 is equal to 0. Yo, that is Euler's identity. Pretty sick, huh? All right, so using the Maclaurin series for e to the x, we can find Euler's formula and we can find Euler's identity. What's crazy about this is that I was just reading up on this. Euler was using Maclaurin series was introduced like 20 years before, or 10 years or something like that, before Euler came up with this. So it's kind of cool that it was fairly recent, fairly young to do all that stuff. It's just, it baffles me. I mean, now we just kind of take it as truth, but before we had to kind of prove all these things and trust that the Maclaurin series were all correct. But here we go. We have the Euler's formula. We have Euler's identity. That is exactly what I wanted to kind of preface with, because now what we're going to end up doing is we're going to go ahead and prove the Basel problem. And again, here is the Basel problem right here. Okay, so the summation of 1 over n squared as n goes to 1 to infinity is equal to pi squared over 6. Now, this is something that we always take as truth. I've seen, or I've helped so many Calc BC students study in series, and we know not only does this converge through the p-series test, but also because this is equal to pi squared over 6. And we're going to talk about, and we're going to prove exactly why this was the case. Okay, so let's go ahead and maybe we can I'll probably leave that page there. So again, we're trying to prove that we have the summation from n is equal to 1 to infinity of 1 over n squared is equal to pi squared over 6. Again, this is what we call the Basel problem. Or Basel. I don't know. Whatever you guys want to call it. All right, so let's go ahead and start off how Euler proved this. So he started off with the Maclaurin series for sine. So if you remember the Maclaurin series, you have x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, on and on and on. Okay. One of the things that he noticed is the fundamental theorem of algebra. So don't forget, I'm just going to put fundamental theorem of algebra. Excuse my bad writing here. But what that says is that if we have a polynomial of nth power or nth degree, I'm just going to kind of write these down all the way to a of 1 plus a of 0 is equal to 0. Then there's going to be at most n roots, whether they're real or complex. Okay, and from that, there's a consequence, which at the time, Euler did not know this. It wasn't proved, but he took a hunch that basically if we take all the roots, then this polynomial is going to be a product of their linear roots. What I mean by that is you have a constant, or this polynomial here is going to equal to some constant times a minus, or not a, x minus r1 times x minus r2, on and on and on, where you have all the nth roots. Okay, this is what he said, or this is what he thought. Okay, so given this fundamental theorem of algebra, then this should be true. This wasn't proven. He just took a hunch. He took a gamble when he said, I'm just going to show that this is hopefully true. And then it wasn't until, I think it was like 50 or 75 years later that someone proved it. It was Weierstrass. But anyway, back to that idea. He said, okay, well, if I have sine of x, I have a polynomial up here, then surely if I find the zeros of the function, then I'm going to be able to write it as a product here. Okay, well, he said sine of x is equal to 0. We got to figure that out. And if you think of the unit circle, this occurs when x is equal to 0, pi, 2 pi, 3 pi, 4 pi, 5 pi, it goes on forever, every multiple of pi, but not just the positives, but also the negatives. So he just is going to say my roots are plus or minus pi n. Therefore, I can rewrite sine of x as some constant times x minus 0, which is the first root, times x minus pi times x plus pi. We're just going to include the positive and the negative so we never forget it. And then we're going to continue x minus 2 pi, x plus 2 pi, and we can continue maybe to 3 pi and then just put dot, dot, dot after that. Okay, again, he didn't know this. He just said, I think this is true, and it was proven later on that this was correct. Okay, a couple of things that we're going to do. We're going to go ahead and simplify this x minus 0. That's just going to become x, so we have k times x, and then we're going to go ahead and multiply these groups. If you notice, these are difference of squares. All right, this is x squared minus pi squared. The next one is x squared minus 4 pi squared. If you don't believe me, do the math, grab a piece of paper, follow along. And then we have x squared minus 9 pi squared, which is pretty sick. And again, we can continue. It will be like x squared minus 16 pi x squared, x squared minus 25 x squared, and so on. All right, but that's the pattern. Well, we need to find the value of k. All right, so before we do that, we're going to go ahead and do something. We're going to go ahead and divide both sides by x so that we have sine of x over x is equal to the constant k times x squared minus pi squared, x squared minus 4 pi squared, x squared minus 9 pi squared, on and on and on. This is so exciting. If you recognize this, this is a very, very unique limit. Or not a limit yet, but this is a function or a trigonometric limit that we should know. And so if we take the limit as x approaches 0 of both sides, on the right side, if we plug in 0 for everything, it's just going to be 0 minus pi squared, so negative pi squared. Let me just talk, so k times negative pi squared, and then we're going to do the same thing here, 0 minus 4 pi squared, and it goes on and on. Awesome. On this side, if you were to prove what this is equal to 1 using L'Hopital's rule. Maybe I can put it here. So remember, the idea is you first use direct substitution. So when you do that, you get 0 over 0. It's indeterminate. Therefore, we're going to use L'Hopital's rule. Derivative of the top is going to be cosine. Derivative of the bottom is going to be 1. Once you plug in 0, then we just get cosine of 0, which is just equal to 1. So we've shown that the left side is equal to 1. Nice. So now what we can go ahead and do is we're going to move all these values to the other side. All right. That's going to give us our value of k. So let me just kind of start off here. So remember, I have this is equal to k times all this stuff. So let's go ahead and divide all these products to the other side, giving us that k is equal to 1 over negative pi squared times negative 4 pi squared times negative 9 pi squared, and so on the bottom. Okay, so then now going back to our function here, now that we divided the x, we have the value of k. Now we know that 1 is equal to, the k value, which is this one right here, okay, which is 1 over this entire thing. So what we're going to do is we're going to rewrite this entire value, and because k is a fraction, we're just going to put these values on the bottom. Check this out. It's going to be x squared minus pi squared, x squared minus 4 pi squared, x squared minus 9 pi squared, all over negative pi squared, negative 4 pi squared times negative 9 pi squared, on and on and on. This is really nice, okay? Because everything just kind of fits in. So what we can go ahead and do is we can divide this into here. And check out what's going to happen. I'm just going to kind of show the work. This is x squared over negative 9, or negative pi squared, minus pi squared over negative pi squared, okay? So what that's going to do is this, the second term becomes a positive one. So I'm just going to put it in the front. And then this is just going to be negative. So I'm just going to do minus x squared over pi squared. And if we do the same thing, divide this into here, it's going to become the same value. Wow, surreal. Thank you for the roses. But please, please, save your money. No need for that. No need for that. But thank you. I appreciate you. You're the best. Beautiful. Let's continue. So I did the first one here with that, and then now I'm going to do the same thing with the negative pi, and hopefully you can trust that there's a pattern here. I've been playing around with this all day today, and I've been finding some nice patterns. But yeah, pretty exciting. Awesome. So let's go ahead and continue. Here's the tricky part, okay? We're going to go ahead and multiply these things out. And unfortunately, there's no shortcut to this, but we're just going to hopefully do it at least 3 times. So we're going to do 1, 2, 3 multiplications and find a pattern, okay? Now, if we multiply the first parentheses using the FOIL method or distributive property, we're going to get 1 minus x squared over 4 pi squared minus x squared over pi squared plus x to the 4th over 4 pi squared. Or x to the 4th over 4 pi squared times pi squared. A little tricky. And then we're going to do the same thing. We still got this second part over here. Okay? So let's continue. 1, you're going to multiply the 1 times every single term in the other parentheses. So that's 1 minus x squared over 9 pi squared. And then we're going to continue. Negative x squared times every value in this second parentheses. So this is going to be negative x squared over 4 pi squared plus x to the 4th over 4 pi squared, 9 pi squared. And I'm going to tell you right now, we're not going to care about the x to the 4ths. We're only going to care about the x to the second part. And the reason for that is because we're going to end up wanting something like this, okay? We're looking for this n squared. You're going to see in a second. This is very exciting, guys. So let's continue. So I multiplied this second part into this. So now the x squared minus pi squared is going to become negative x squared over pi squared plus x to the 4th over pi squared, 9 pi squared. Last one, I promise. X to the 4th times these two terms is going to be plus x to the 4th over 4 pi squared times pi squared minus x to the 6th over 4 pi squared, 9 pi squared. I'm telling you, we don't care about the x to the 4th, x to the 6th. We don't care about this. But hopefully you can see a pattern. Let me kind of group these, especially the x squareds, okay? So if I group the x squareds, I have 3 here. I'm going to put them together and in some order because I see a pi squared, I see a 4 pi squared, then I see a 9 pi squared. So I'll do negative x squared over pi squared minus x squared over 4 pi squared minus x squared over 9 pi squared. And technically, if we continue this process, we should see this pattern on and on and on. Okay? Let's forget about the x to the 4, it's x to the 6. You'll see. Trust me. I'm not even going to, I'll just write them down. Let's just imagine there's x to the 4 powers, and then there's the x to the 6, and so on. Again, we don't care about that. We care specifically about the x squared. You're going to see in a second. So now what we're going to do is I'm noticing that there's somewhat this is 9 pi squared. There's somewhat of a common factors. There's an x squared over pi squared as a GCF in here. So let's go ahead and factor it out. So we have 1. And all these are negative, so let's factor out a negative x squared over pi squared. And what do we get? 1 minus, or plus, 1 over 4 plus 1 over 9. And this should continue for the x squareds. Again, disregard the x to the 4s and the x to the 6. They're there, but we don't really care about them. So now, check this right here. Check this out. You notice this? I can find a nice series for this, giving me the summation from n is equal to 1 to infinity of 1 over n squared. Holy shit, guys. There it is. This is a series that Euler found and said, oh my gosh, I think I know what this answer is. Okay? So, as we had mentioned, I don't know why there's a 1 here this whole time. That was just for the limit. This entire thing should be sine x over x, sine x over x. My bad. So we have sine x over x is equal to this entire thing. So let's go back and revisit the Maclaurin series, and let's use this for a second, okay? I'll flip, I won't flip the pages. I'll do this and this. By the way, I'm thinking that I can, write these every time I do lives, kind of have this, staple them together, and then just give them away as a gift, whoever wants to look at my notes. I think that'd be kind of fun to do. But anyway, let's continue. Okay, so as I mentioned, right now we have sine of x over x is equal to, we said 1 minus x squared over pi squared with the summation here. And of course, there's other parts to that. There's like the x to the 4th, the x to the 6th, and so on. We don't care, okay? We only care about the x to the, or the x squared coefficient because that's the summation that we want. All right. Nice. Yeah, I think if anyone is in the U.S., I'd be happy to mail them. But yeah, I'm thinking of doing that. I think that'd be kind of cool. All right, so let's go ahead and just revisit the sine x over x real quick. So remember, sine of x is equal to x minus x cubed over 3 factorial plus x to the 5th over 5 factorial plus x to the 7th over 7 factorial, on and on and on. If we divide an x into that, just imagine we're dividing x into every single term in our Maclaurin series. We have sine of x over x is equal to 1 minus x squared over 3 factorial plus x to the 4th over 5 factorial plus x to the 6th over 7 factorial, on and on and on. We don't care about that because look at this. This is the negative x squared term, and then we have the negative x squared term, and these are both the same because this is sine of x over x. So we can say that these two are equal to each other. So we can say negative x squared over 3 factorial is equal to negative x squared over pi squared, summation from n is equal to 1 to infinity of 1 over n squared. Okay, we don't know what this is, obviously, but here's what we can do. We can go ahead and cancel out the x squareds, cancel out the negatives, and then simplify this 3 factorial. So that's 1/6 is equal to 1 over pi squared, summation n is equal to 1 of 1 over n squared. Yo, let's go ahead and multiply the pi squared to the other side, and we have the solution to the Basel problem. Euler, in 1700, I think, found this. He found this out by simply taking a gamble in the very beginning using the fundamental theorem of calculus. And eventually, he got to this answer right here, which is pretty sick. And I've been playing around with this summation here, and I don't know if this is correct, but I've been getting something like pi squared over 1, or pi to the 4th, over 120 is equal to, and I'll write this down, summation from n is equal to 2 of 1 over n squared, 1 over n squared, pi squared over 6, minus summation of k is equal to 1 to n of 1 over k squared. And then I think it was like plus pi squared over 6 or something like that. I think that these are equal to each other. I haven't been able to prove that though. Okay. I was looking at it. I posted on Instagram, and I'm hoping that someone can correct it. But I think this is what it is. Maybe I can talk about that later on. But anyway, we have proven the Basel problem. Okay. Someone was asking about integration, and that is exactly what we're going to do. I have two integration tricks that I kind of want to show you. Okay. So far, just keep in mind, for those that are just tuning in, we have been doing, or we talked about e to the x, starting with the Maclaurin series of e to the x. We've shown how we can get not only the Euler identity, but Euler's formula for polar coordinates or complex values. Okay? I barely know algebra. It's all good. This is all about following along. To be honest, I am just scribbling away because I saw something that fascinated me yesterday, and it's paid off. This is kind of cool. To be honest, this is how you learn. You're teaching yourself the material, and that's kind of what I'm doing here. So two integrals that I specifically want to solve using Euler's formula is we're going to solve integral of e to the x cosine of x dx, and we're going to solve the integral from negative infinity to infinity of sine of x squared dx. And we're going to show how this is root pi over 2. Okay, so we're going to go ahead and use the Euler formula to solve this. So I'm going to say using Euler's formula. And remember, Euler's formula is I e to the x is equal to cosine of x plus I sine of x, which is really cool. Again, we already proved this. All right, so we talked about the Taylor polynomial or the Maclaurin series for e to the I x and how we got this answer. Okay, someone's asking if I could go over Taylor and Maclaurin. You know, maybe I'll do that on the next live. Right now, I really just want to talk about this technique here, okay? We got the ball rolling. Look at this. We got 1, 2, 3, 4 pages. We're probably going to have 6, 7 pages. We'll see. But yes, I will definitely go over that. Maybe I can make a video about it. Anyway, so one thing to remember or to keep in mind is that, again, this is a complex value. You notice we have the real part, and we have the imaginary part because that's the one attached to the I. So this is the imaginary. I'm just going to put IM. So sometimes in math, we'll write the real of e to the ix. And what that means is you want to take the real part of this Euler formula, and that's going to be the cosine because that's the real part. If I write imaginary, then that's going to be the sine of x. All right, so it's important to kind of understand that. And this is going to be something that I'm going to talk about. Okay? So let's continue with that. So now we're going to go ahead and solve this. And I can tell you right now, you can solve it using integration by parts. If someone wants me to solve it using integration by parts, I can do that. Otherwise, I'm just going to continue and talk about how I'm going to solve this using Euler's formula. So let me know. I want to hear in the chat, do you guys want me to hear, or you guys want me to solve this integration by parts just to show you how to solve it, or do you want me to solve it just using Euler's formula? Oh, okay. Blue Trash Panda said both. All right. I guess we have to do both, right? And we're going to do Euler's formula. So let's go ahead and do IVP first. So integration by parts. This one I like to call, and I think I mentioned I have in my book of integrals, is you do ultraviolet voodoo, in other words, integration by parts, but move that shit to the other side. And here's what I mean by that. So we're going to start off by using integration by parts. So we're going to make our u equal to e to the x. Our du will be e to the x cosine of e to the x dx. What is wrong with me? dv is your cosine x dx, and then your v is just going to be sine x. So now, using integration by parts, we have this integral, e to the x cosine of x, is equal to uv, so e to the x sine of x, minus v du, minus sine e to the x. So integral e to the x sine x. I'll just kind of write it in that order. All right, well, it seems like we're sort of stuck. Okay? Yeah, ultraviolet voodoo. I love using that. Much better than integration by parts. I make a whole joke about that in a book of integrals. But let's continue. What we have here is still e to the x sine of x, so we can't really solve it yet because we still have to continue integrating that. Well, I think we already knew we were going to have to integrate again, but it looks like we're going to have to use integration by parts one last time. So u is equal to the e to the x, du is equal to e to the x dx, dv is sine of x dx, and v is negative cosine x. Okay, that's the integral of sine x. So let's continue. Now we have integral of e to the x cosine x dx equals our first value, e to the x sine of x. Now be very careful here. This is minus the integral of this. So minus our uv, which is negative e to the x cosine x, minus integral of v du. Now, v is already negative, so when I have this negative sign, that's going to turn positive, and we have e to the x cosine of x dx. All right, let's continue. So what we have right now is we have integral e to the x cosine of x dx equals, let's go ahead and write down the rest, e to the x sine of x, and let's distribute this negative sign. So this negative sign, when you distribute it to the first part, that's a positive e to the x cosine of x, and then this one becomes negative times a positive, so negative integral e to the x cosine of x dx. So check this out. You notice that this is the same thing as this, and that's what I meant by move that shit to the other side. Let's go ahead and add this integral to this side. Okay, so that's like integral e to the x cosine x, and I'm adding it on this side, e to the x cosine x dx. Now, these are the same terms. So this is 2 integral e to the x cosine x dx, which is the integral that we're trying to find. And we get something on the right side that's just in terms of e to the x, or it's just in terms of x. There's no integrals here. Don't forget your plus cheese on there. And now, one last time, let's go ahead and divide the 2 to the other side. So we have the integral that we were looking for equals to e to the x sine of x over 2 plus e to the x cosine of x over 2. And then when you divide your cheese divided by 2, that's just going to be still a constant. That's our integral right there. That's integration by parts, okay? But let's go ahead and talk about the real party here. So remember, e to the ix is equal to cosine of x plus I sine of x, okay? So if I'm just working with the cosine, I think we mentioned this, and if you're just tuning in, I'm calling for the real value of the real part of that. So that's just going to be cosine x. Okay, so again, the real value of this Euler formula is just going to be cosine of x. And by the way, guys, if you have to leave, don't forget, I put all the replays on my YouTube, and I think I'm going to put it on my Instagram as well. So you're more than welcome to check my YouTube and just see that, the replay. Okay. So we have the real part of e to the I of x is cosine of x. So if I'm going to go ahead and write this integral, all right, so then what we're going to end up getting is integral of e to the x times the real part of e to the ix dx. Now, this is the confusing part. And to this, like, I'm still trying to wrap my head around this, because this real is not necessarily a function. There's just saying the real part of this. So if I were to multiply the ex to this, I can put the real, or I can put it inside the real part, or inside this real, because e to the x is still a real part. So when I multiply by another value, I mean, I'm still going to get the real part. So it's fine. Okay. But the tricky part about this, and again, I'm so uncomfortable doing this, but you pull out the real and just put it on the outside, basically saying, hey, integrate this, but at the very end, you're going to get a complex value. So you're just going to give me the real part of that complex value. And we'll talk about what that means in a second. Okay, so we can go ahead and combine these using properties of powers. And check this out. This is going to be 1 plus I x dx. All right, maybe I can write this here on at this end. We're going to go ahead and integrate using u substitution, just so everyone can sort of see how this is going. So u is going to equal to 1 plus I x. So remember, I is a complex number, yes, but you know what? Don't worry about it. Treat it almost like a constant, because that's basically what it is, just in a complex plane. So this is 1 plus I dx. So then my du over 1 plus I is equal to dx. So then now I can go ahead and rewrite my integral, the real part of integral of e to the u over 1 plus I du. Now, I know it says real, so you can say, well, this cancels out. Don't worry about it. We're not going to find the real until the very end. Okay? Math joy, yes. Love your stuff, dude. All right, so let's go ahead and continue. We're going to go ahead and integrate this. Now, this is just e to the u, so this is 1 over 1 plus I, e to the u plus your cheese. Okay? So whatever this is, 1 plus I, e to the u plus your cheese, we're going to go ahead and substitute the u back in. So remember, whoops, let me put this in the back. Remember that our u value was 1 plus ix. So we have integral of e to the x cosine of x dx is equal to the real part of 1 over 1 plus I e to the 1 plus I x plus c. And you might think, dude, all these are reals. How are we going to get our answer? You're going to see in a second. This is going to be exciting. This is why Euler's formula is so powerful. Okay? And keep in mind, I'm just going to kind of leave that worksheet. I want to see where I left my answer. Oh, here we go. Okay, so my answer was here. I'll come back to that one. Okay, yeah, you can integrate I as a constant. It's totally fine. But again, we're going to take care of all this in a second. First thing that we're going to deal with is 1 over 1 plus I. Okay, so 1 over 1 plus I, if you remember how to divide your complex numbers, we multiply by the conjugate. This is going to become 1 minus I over, now check this out. If you use the FOIL method, this is just 1 minus negative 1. So we can add these together, making it a 2. So this is 1 plus I over 2. Okay, you're like, that doesn't really help, but you'll see in a second. All right, the whole point is we don't really like complex values as a denominator, so we like to switch those. So back to our integral, we said this is equal to the real part of this. So we have the real part of 1 plus I over 2 times e 1 plus I x plus our cheese. Now, a couple of things that we're going to do is just rewrite this a little bit. We're going to do 1/2 plus I over 2. I just divided everything by 2. And in this part, I'm going to write it as e to the x times e to the ix, kind of just working it out since the very beginning. Okay? And then we still have our plus cheese. So now let's go ahead and distribute these values into both of these terms. So we have the real part of 1/2 e to the x e to the ix plus I over 2 e to the x e to the ix plus our cheese. So let's talk about this real quick. Remember, e to the ix is cosine of x plus I sine of x. And then same thing on the other side, I over 2 e to the x times cosine of x plus I sine of x, and then plus our cheese, and we're almost done. We're going to go ahead and distribute this 1/2 x or 1/2 e to the x to both of these terms. So that gives me, I'm just going to write it like this, e to the x cosine of x over 2. So I just put it as one denominator here, plus I e to the x sine of x over 2. Don't forget this is still the real part. And then plus, let's continue here. When we multiply this value to the cosine, this becomes I e to the x cosine of x over 2. And then we're going to multiply this to this side. Okay. I just want to make sure, did I have my answer correct? Oh, someone was talking about, yes, someone was mentioning. Oh my gosh, I should have read that. So when I wrote this, 1 minus I, my answer, for some reason, I wrote it as 1 plus I. This is a minus, meaning that all these values are minuses. So the only thing that we should really be careful with is when we distribute, this should be a minus, this part should be a minus. So that should be a negative value. So when I multiply it to this becomes negative I e to the x cosine of x. Oh my goodness. Yes, Peruvian beans, dude. Thank you. Thank you. Oh yeah, yes, thank you. Oh my goodness. I saw that. I'm like, oh, you guys must be explaining something to someone, but thank you very much. These constant typos will kill you. So got to be really careful. I noticed that I made a mistake, and you'll see why, because this value has to be positive, and you'll see that in a second. So when I multiply the negative I over 2 e to the x times this I sine x, this is going to become, I still have the constant, so e to the x sine of x over 2. But then when you do negative I times I, that's going to be a positive, or a positive 1, and then plus our cheese. And this is what I mean. We get our answer. There's no more, well, there are some constants or some imaginary numbers here. However, we're looking for the real part. So guess what? Be gone with these. We don't care about these. These are the imaginaries. All we care about is our solution in the real part. And in our plus cheese. Chat, that was exactly what we found using integration by parts. The only thing is that this was sine was first and then cosine was second. It's the same thing. Cosine, sine, I just flipped these. They're the same thing. How sick is that? How sick is that? So 1, integration by parts. 2, Euler's formula. Now, you might think, okay, that was way too long. And it was, but I think it was a good exercise. But that's going to leave me with my final integral of the day, and then we'll come back. This has been exciting. This is the first format I did where like I'm just picking a topic and I'm kind of building on it. And look at that, all these notes. Wow, all these notes. I think, again, I think I'm just going to end up like stapling them and then put like, you know, live, whatever, and then just whoever wants them. Ah, there you go. Yes, Gabby, you got him. You got him. Gabby, if I forget, please follow me and DM me real quick so I have that. I'm going to try to take a screenshot of your email here so that I can send them. Gabby, you got dibs. You got dibs. Okay, so here we go. Very last one. So now we're going to go ahead and integrate this value here. Whoops. The integral from negative infinity to infinity of sine of x squared dx. And we're going to show how this is root pi over 2. Okay? So we're going to say using Euler's formula. And you'll see in a second how this is going to be so powerful. By the way, whoever gets my notes, Gabby, and anyone else in the future, I'm so sorry about like my writing. That's just how I write. All right, let's continue. So let's talk about why this is equal to root pi over 2. So the first thing that we got to remember, and something that I don't want to prove on here, I guess I should have proved it, but there is an integral, negative infinity to infinity of e to the negative x squared dx, and that's equal to root pi. And then technically this integral typically has an a right in front of it, so negative a x squared, and that's equal to root pi over a. This is what we call the Gaussian integral. And I think I made a video about this. I also, by the way, if you don't follow me on Instagram, please do, because I post a lot more like detailed stuff. Okay, just keep that in mind. Awesome. So we're going to use this Gaussian integral. How do we turn this into this? Well, we already know there's a relationship between e and sine, and that's the Euler formula. So we're going to go ahead and do a couple things. This is our Euler formula, once again. So I'm going to put using Euler formula. Now, we want a couple things. We want an x squared. That's definitely what we want. And then we need the negative. So we're going to go ahead and introduce a negative I x squared. We're just going to change the input values. So this is cosine negative I x squared plus I sine negative I x squared. Now, you'll notice that, why am I, oh, this is so wrong because why are there i's? I knew something was wrong. I'm so sorry. So the Euler's formula just tells you that whatever you change for x, that goes into your inputs for cosine and sine. So negative I x squared, I'm changing the input for cosine into a negative x squared, and then I'm changing the input for sine into a negative x squared. All right. And so what happens here is we have e to the negative I x squared is equal to cosine x squared. Why? Because this is just going to be, this is even, so it's just going to be cosine. And then this is negative, so negative I sine x squared. So James, you're asking if the Gaussian integral is assumed? Yeah, so sometimes, and I used to, not like it. I used to not like this Gaussian integral because this was just a formula that was given to me. And if you know how to prove it, I think it's really, really interesting and very helpful to use. Okay. So for the sake of this, I'm definitely going to use, I want the sine because that's what we're looking for. I was going to change it to cosine, but let's just use the sine. Okay. So the way we do this is we multiply everything by an I, so that we can get I cosine x squared. And then when you multiply the I times this negative I, it becomes negative negative 1. So that's plus sine x squared. So now the sine becomes your real, the cosine becomes your imaginary. So going back to this integral, what we're really working with is we're working from the integral from negative infinity to infinity of I e to the negative I x squared dx. Okay, that's really cool. Oh, and don't forget, this is the real part. So we got to remember that we're working with the real part. All right, so let's continue. This is technically, remember, as a constant. So we have the real of I from integral from negative infinity to infinity of e to the negative I x squared dx. And looking at the Gaussian integral, this is equal to root pi over I. So in this case, we're going to have I, and this is going to be root pi over, I said I was already talking about that, but whatever the a value is, or the constant in front of the x squared, that's what's going to go underneath the root. So back here, it's just going to be pi over I. All right, so let's go ahead and finish this off. Okay, so we have the real of I pi over I. And you might think, okay, well, yeah, we're done. Like, we can't really do anything about this. However, we can do a few things. Okay, first things first. By the way, did I have a negative on here? Was there a negative anywhere on here? I don't think so, right? I think we're good. Okay, so first thing that we're going to do is we're going to focus on the denominator. That's the I. So that's 1 over I. Okay, so let's simplify that. If I multiply both the top and the bottom by I get I squared over negative 1. Geez, I can't believe I couldn't even solve that. In this case, that's just going to be negative 1 over 1. Am I okay, guys? Oh my goodness. Let's do this again. Let's multiply the I to the top and the bottom, and we get I on the top over I times I, so negative 1. So basically, this is negative I, which is okay, because now what we have, the real of, we have I, and then we have negative I, and then pi. Okay, and that's okay. All right, because we're gonna start doing some stuff. Now we're gonna go to the polar form and think about this. I is up here, and the polar form for that is I, or e to the I pi over 2. If you know some polar form, hopefully that makes sense, but trust me, this is exactly what it is. So we have real of I, e to the I pi over 2, and on the inside we have negative pi. Negative, or not negative pi, negative I. Negative I is over here, and so that's just going to be e to the I negative pi over 2. I can technically do 3 pi over 2, but I'm just going to do a negative pi over 2. It's going to be the same thing. So I have e to the I negative pi over 2, and then still the times pi. Now, one thing you got to remember is that whenever you have these terms and you take the square root, this is just going to become e to the I pi over 2, e to the negative pi over 4. And there's an I there. I'm so sorry. Times root pi. Okay, we're almost done. Now, we're going to go ahead and add these things. This is pi over 2 plus negative pi over 4. Okay, so let's go ahead and get some common denominators here. I'm going to go 2 pi over 4 minus pi over 4. This is just pi over 4. Okay, all I did was get common denominators, because now I have the real of, if I combine these two, this is just e to the I pi over 4 root pi. And remember, using Euler's formula, this is cosine of pi over 4 plus I sine pi over 4 times root pi. Two things that I'm going to do in this step. I'm going to distribute the root pi into both of these, but I'm also going to simplify the pi over 4, or the cosine of pi over 4. Cosine of pi over 4 is root 2 over 2 plus I root 2 over 2. And then you still have the root pi. I know I said I was going to do that in the same step, but I'm just going to do it now. So I have root 2 pi over 2 plus I root 2 pi over 2. Okay, but it's only calling for the real part. So again, no imaginary, we just want the real. Therefore, we can say that this integral of sine x squared dx is equal to root 2 pi over 2. Okay, now if I want to get, or if I wanted to look like the answer that we had, because remember, we wanted to show, where is my paper? Oh, right here. We wanted to show that this integral was root pi over 2, all on the inside. We're going to do this. We're going to turn this root 2 into root 4. So we have root 2 over root 4. We could put it together, and that's just going to be root pi over 2. that is our value. This right here, we have shown using Euler's formula and the Gaussian integral, which is something that I should have done or should have explained maybe in the next live, but that is our integral there. Look at that. Hold on, let's put it here. So guys, look at what we did. Okay, we started off with e to the x, and we proved, or we showed how we can get Euler's identity and then Euler's formula. And then we talked about the Basel problem. Okay, here it is. Here are the notes, and we showed how that was equal to pi squared over 6, which was amazing. And then we talked about how we can use integration by parts to solve this, but then most importantly, we talked about how we can use Euler's formula to solve for that integral, which was this part over here. And then we said, you know what, from there, we're going to go ahead and prove this integral here. This is called Fresnel integral. Not something that you could easily solve, but we use Euler's formula for that. Okay. Pretty simple, guys. And that was it. And Gabby, if you're still here, I'll send these to you. I'm going to staple them. And I think every live, or hopefully I can build something like this. This has been my favorite live that we've done. I mean, I've been able to group the things that I've learned today and just write them out. And hopefully you guys can build a connection. Okay, someone's asking if I'll have a book of differential equations or polar integration. You know, I think I'm going to be able to do that soon. I'm working on a calculus prep book, so polar integration will be there because it involves Calc 2. And maybe later on we'll do some differential equations. But yeah, we'll see. We'll get there. Okay, hook me up with a copy of that integration book. In fact, Elias, if you go to my Instagram, there is a story right now that's still going on. I am giving away 3 free physical books and then 3 free bundles. So the physical bundle, you get the calc book or the derivative book. You'll get 2 integration books, and then you get like an areas book and limits. So 5 books. So go to my Instagram, go to my stories, and you'll see you'll see the instructions there. Someone's asking if I studied applied math. I studied pure math. I initially I went as an electrical engineer, and then I was asking too many math questions, and my professor said, you are bound to be a pure mathematician. And that's what happened. All right, y'all. I mean, hopefully, I just kind of want to show you, these are the notes that I typically like to write. Sometimes I just think of ideas, or I see problems online, and I work them out. Well, there you go. And then I just think of stuff that I want to talk about on my live. And so hopefully I'll continue to do that. I think this is always fun. I think live should just be like, not necessarily a throwaway, but a quick chat. And yeah, just talk about stuff like this. Hardest math I ever taken, to be honest, topology, not theory. Maybe if I go back and study it, I would understand it. But you know, with the group theory, ring theory, I think that was just super hard. No finance math, no master's or PhD. I am way too dumb for that. Yes, the best way to learn math, or you're taking college math, is just pick up a book and start writing stuff. I mean, listen, look how many notes I just took right now. I took 7 or 8 pages of notes, and this was just me thinking about like, I could connect this and that, and really I just had topics that I wanted to talk about on the live, and you kind of like talk them out and you get better at it. I think that's the best way to really improve on your math skills, is to just practice as many problems as you can and then just, talk it out. I think that'd be great. I think Calc 3, in my opinion, well, it's all going to depend. If you have a strong Calc 1 and 2 base, so I'm talking like your algebra is really strong, then Calc 3 is going to be a breeze, because you're really just doing the same ideas. You're just now working with like partial derivatives and double integrals, and that could be a pain. But I think if you have a solid understanding of Calc 1 and 2, then Calc 3, that transition shouldn't be as difficult. All right, y'all. I'm going to head out, but I'm going to see you guys real soon. I'm going to think of like some other topics that we should talk about. And I think that'd be great. I'm going to use the live, not only during like calc time or AP calc, I'll probably do some AP prep, but for the most part, I'm just going to do like just math talk. I mean, I always try to think of all these different ideas, and I'm just going to write them out. If I make mistakes, then so be it. I mean, that's the point. This is what we're going to do out here. Thank you. All right. Yeah, I like this one too. This was fun. We'll continue. And, I'm going to switch. I'm going to go from TikTok to Instagram just to see which one works best. So if you guys follow me on Insta, or if you have not, please continue to follow me on Instagram because I post different content on there than I do here on TikTok. TikTok is more chill, and then Instagram is like more artistic. Awesome. All right, y'all. Well, I'm going to take off. Oh, someone said we need your notes. So one day, Gabby has these ones, but I think every live, I'm just going to staple them together and then like give them out to someone. Yeah. All right. Cool. So I'm going to take off. Hopefully, I'll see you guys. It is Monday, maybe Thursday or something like that. I'll try to keep a consistent schedule, but we'll go from there. Otherwise, replays are always on my YouTube. You can watch them there. Hope you guys have a great day. I'll talk to you real soon. Peace. Before I leave, can I make it in a PDF? Maybe. All right. Take it easy.